Hey programmers, welcome back. Right now I want to go over a JavaScript solution for this tree includes problem, right? And we'll solve this both depth first and also breadth first. And I think we'll start with the iterative breadth first version. And so this is really just going to be an implementation of the classic breadth first search algorithm. So I'm just going to lay down my classic breadth first traversal code and then just add some conditional logic afterwards, right? So you should be familiar with it by now, but for my breadth first traversal, I'm going to use a queue. So I'll say const queue equals an empty array, or really an array with the root thrown on the inside. And from there, I have my main algorithm, right? So I loop while my queue is not empty, so while queue length is bigger than 0, then keep on going. And on a single iteration of this traversal, what I do is queue.shift, so remove from the front of my queue, or the front of my array, remove the first element. And I'll save that into a variable called current. So that will be just an instance of node. And for now, why don't I just build up my solution slowly? I'll just, console.log what current.val is. But once I consider this node, what I want to do is really add its children into my queue. Only if they exist though, right? So in general, I'm going to write like queue.push. So I'm going to add to the back of my queue so I get a nice queue order, push the left child, so current left. Likewise, the right child. But imagine that I have an asymmetric node or just a leaf node, right? Something like C would only have a right child, so its left would be null. So if current is C, then I'd be pushing null into my queue as the left, which is no good, right? And so I need to guard here and only push the children if they exist. So something like this, hey, if the current has that corresponding left and right, then I can go ahead and push it. So this is looking pretty good. And that should actually be the main traversal part of the code. So I'll just test this manually. So very manually, so maybe just this call. So I'm not going to return booleans yet. We'll build up to that, but I should at least see my values printed. If I kind of run this manual test case, I'll bring in my node class. I should see the values printed in a correct breadth first order. So that means A, B, C, D, E, F. Recall that breadth first traversal travels across our tree before going lower. So it must finish a level before traveling to the next level. So let's just run this manually as a script. See what we get here. A, B, C, D, E, F. Nice. So I'm getting the right order of traversal. And now I can work in, I think, the conditional logic, because they want us to return booleans over here. So pretty straightforward stuff. We'll go ahead and check. Once something leaves the queue, I can check if the current node's value is equal to my target, then I've found the thing I'm looking for. So just return true, right? You're done. You don't need to travel through the rest of the tree because you can return true. But on the flip side, if my value that I'm currently at is not the target value, then I must continue looking through the rest of the tree, right? So if I finish the entire while loop, that means I've traveled through the entire tree and I never found the thing I'm looking for, I should return false. So I need a late return false over here. A really common mistake people tend to make is what you don't want to do is just do like else return false here. So this is going to be wrong, right? Because this would only check like the very first node. This would only check the root, and then you check if the root is not equal to the value. If it's not, you just return false, which is not really useful because it could be somewhere else in the tree. So you're going to need that late return false pattern over here. But with that, I think we're going to pass some of the test cases. So I'll run the test cases by hitting that test button. And there's probably one scenario we did not foresee. Cool, and there it is, right? Cannot read property val of null. We're failing test 05. If I look at that spec, test 5 gives us the null node as our root, right? So just the empty tree. You cannot find the B character inside of the empty tree, so return looks like false over here. And so I can just handle that one explicitly. I'll go ahead and check at the top. If my root is null, right, if that's the case, then just return false. So I can't possibly find any target in an empty tree, right? The reason our code was failing before is if root is null, then I initialize my queue with null, and when that thing is popped, when that null is popped, or rather shifted from the queue in the first iteration, then I check null.val, which is an illegal JavaScript operation. So I'll run all these test cases now. Nice, and there we have our breadth first solution for this tree includes problem. All right, now let's work on the recursive depth first version of this. And it's actually my personal favorite because it utilizes a pattern that I think is quite elegant and one I use a lot for much more difficult problems. So like we said in the approach video, if you haven't watched the approach video, you definitely want to check it out for this recursive version, right? What I should do is check, hey, if my root is null, if I have the empty tree basically, then just return false, right? Because I can't possibly find my target in an empty tree, right? That's just a given. And from there, I know I'm going to have the general shape of some just depth first traversal code, which means you call the same function because it's recursive. That's what recursive means. And you pass along your root.left and a separate call, your root right. And what I should be sure to do is don't forget to pass in your target, right? The target that you're looking for never changes. And I know that these two calls are going to give me back Boolean data. And I know that the Boolean I get back from like this call would represent whether or not I found the target in that subtree, right? So this gives me the result of if I found it in the left subtree or the result if I found it in the right subtree. And I can just do the logical OR on both of these, right? So if I find it in either subtree, then return true. So I could just write an inline return true over here, right? So let's say it's in my right subtree. Then this left-hand side evaluates to false, and this is true, in which case this entire thing evaluates to true. And let's say in the bad scenario, let's say it's not found in either subtree, so this evaluates to false, this right-hand side also evaluates to false, false or false gives me false. However, one thing I need to be sure to add is also an additional base case. After I check if my root is null, what I want to do is then also check, hey, maybe this root I'm currently at, maybe it actually has the target, right? So if root val is equal to the target, then you're also done, except you can return true. Cool, and that was very reminiscent of our approach video. So let's give this a shot. We should be able to pass. Nice, and I love how clean this code is. I will admit, it's pretty tricky if you're not a fan of writing recursion, in which case I'll totally convince you into being a fan of recursion. But notice how kind of clean this code is. It really leverages recursion. One very important thing I want to bring up is it's really keen that I put this base case on line 26 after the null check, right? So let's say I flip the order of these. Let's say you did this. I believe that would not work out always because it assumes that you even have a root, right? So I'm feeling a test 0, 0, but in general, if you look at this code, let's say that root was null, right? You're going to start by checking null.val, and that will throw an error, right? Cannot read property val of null. So you want to actually always lead with your base case that checks if your root is null, right? Because that should guard really the entirety of our code. So this is actually the code you want over here. All right, programmers, so that's all I got for this tree includes solution. I want you to practice both versions, and I'll catch you in the next one.